Hi everyone, welcome back to this channel. Today, we are going to break down how a massive system like Uber works, how it finds drivers, handles millions of ride requests in real time, and still stays lightning fast. We will start from the functional requirements, what Uber actually needs to do, and then go deeper into non-functional aspects like scalability and low latency. So, let's first start with functional requirements. First functional requirement is basically users should be able to find rides from location A to location B. Once they find the ride, they should be also able to request a ride. And third, drivers should be able to accept or deny a request based on all the available requests they are getting in. Now, Uber is a huge system and there are a lot of other things goes on, which is like what type of car you want to choose it. Or there are other few things which is like users and driver, they have to log in or sign up to request a ride, as well as like ride history and cancel ride. We are not going to discuss about those functional requirements in this video. We will just focus on the main core functional requirements. So all other things are out of scope for now. Now, in terms of non-functional requirements, first thing is low latency. Low latency is very important in Uber because if we delay any request here, as an example, let's say like driver gets the request 10 minutes after the actual request, there might be a chance that driver already booked something else. Or there might be a chance that by that time, driver is already at other location. So low latency is very important. Second thing is consistency. Consistency is also very important and specifically in this part because we don't want to double book the driver. Third, high availability. We would like to make sure the system is available all the time. And fourth, scalability. We would like to scale the system and support millions of users, millions of rides in the future globally. So these are the functional and non-functional requirements which we are going to focus on in today's video. Now let's discuss about high-level design. In high-level design, we are going to focus on the main core flow, core functionality of this system. And Uber works very differently compared to all other systems because Uber has like two different types of flow. One is rider flow and another is driver flow. So first, we are going to focus on rider flow. This starts with rider app. Basically, from rider app, you can find or send a request in terms of like finding drivers. It sends requests like current location, destination, ride preferences, etc. And rider app also receives list of nearby drivers, ride confirmation, real-time driver updates, etc. Now, for first flow, which is like find rides. So in this case, the request will go from rider app to API gateway. API gateway basically like it doesn't just route users from API gateway to backend, but it can also handle many more things, which is basically like authentication, rate limiting, etc. So API gateway we can use for multi-purpose, and here it acts as a reverse proxy between mobile apps and backend. So from API gateway, the request will go to find service API, or I would say find ride service. And find ride service will send requests to driver location cache. Basically like driver location cache will have data related to driver, and it will have latitude, longitude, or driver's basic information, etc. And that's how find ride service will find all nearby drivers. Once it has all nearby drivers, then it will send requests to matching service. And matching service, I would say, this is the brain of the system. It receives list of all available drivers from find service, and once it receives all the list, then it applies logic in terms of to match the actual drivers which will work best for the rider. It applies filter by ride type, UberX, UberBlack, etc. And then it also sorts by ETA, driver rating, or price, etc. Now, once it gets all the matching criteria, it matches all the criteria, then only it gives you the actual available drivers list. And once the user requests the notification or user requests the driver, then matching service sends notification to a driver in terms of user's request. So from matching service, the request goes to notification service, as well as at the same time, it sends that particular requested data into the database, where in database we will say a particular record, which is basically like X rider has requested a ride from location A to location B for this particular driver and status requested. So that's one entry goes in database, and here another side notification goes to the driver, and via push notification, driver gets the request detail. Once driver gets the request detail, then driver can decide if they would like to accept or deny the request. So this is how the whole flow end-to-end works from the either side. Now, let's look into driver app. So driver app basically like it has multiple purpose. Our first purpose is we also need to update driver location cache. That is first thing. And second thing, once driver gets the request, then it should be able to accept or deny the request. So how does driver location cache gets updated? Basically, driver app periodically sends heartbeats to driver location cache, and that's how driver location cache gets the data in terms of driver's information. And because of this heartbeat, also driver location cache knows if the driver is still available or not, because it doesn't get heartbeat after, like, let's say 30 minutes or 1 hour. It means that driver is offline, is not working, he or she is not working. So that's what like driver app does, periodically sending heartbeat to driver location cache. That's one part. And second part is like, let's assume that driver already got the request and they are going to accept or deny it. So in that case, how flow works is basically from driver app, the request goes to API gateway. From API gateway, if driver had accepted or rejected, the request goes to matching service. Matching service will update the database, which is like, let's say if they accepted it, then it will change the status to accepted, and if they denied, then it will update the status to deny. As well as it will also update the cache, because once it updates the cache, basically we will update in terms of driver's availability that, okay, this driver is available or not. Let's say if any driver accepted it, it means that driver is not available anymore. So it updates the cache as well. And once the matching service gets the status update, it sends the notification service. And from notification service, another push notification goes to rider app, where this notification notifies particular driver that your request is accepted or rejected. So this is how our driver flow works. Let's dig into our deep dive. In deep dive, we will first go with the scenario find rights. So for find rights, what's the most important thing is having driver location cache. This is the very most important part. If the location cache is not updated, we can't find rights. Basically, we can't find drivers properly. So to get driver location cache, what happens is basically driver app keeps sending heartbeats every few seconds to driver location cache, and that's how we get the latitude and longitude. So in this case, whenever we send GPS coordinates from driver app, we should be saving driver ID, latitude, longitude, timestamp, and status. We need to store data in a way that supports fast geo-based lookups, frequent updates, and efficient filtering. Now, this is where geospatial indexing comes in. And there are multiple concepts, and we are going to discuss about 3 different techniques for geospatial indexing concepts. One of the first technique is Redis Geo. Redis provides built-in support for geospatial indexing using sorted sets under the hood. And basically how it works, each driver's location is stored with the geohash key. So Redis uses geoadd to insert. You can add latitude longitude with driver ID using geoadd command, and to find nearby drivers, you can use georadius and pass latitude longitude, and you pass what distance you want the resource in. Basically, like if you want all the drivers within 3 kilometers or 3 miles radius, then pass that like, okay, georadius, latitude, longitude, and 3 miles. So in that case, it will return all the results on the drivers within 3 miles radius. And why Redis Geo is powerful? Because it is extremely fast in memory data. Second, simple API for Redis queries. And third, is ideal for real-time use cases like driver matching. There are certain limitations with Redis Geo too. One of the limitations is no cross-region queries. Basically, that's one of the limitations. Second is we must implement sharding manually for different regions or city. And third, for in-memory data, it is more expensive at global scale. So this is how Redis Geo works. Now, let's look into our second technique, which is basically like PostGIS. So PostgreSQL has its own geospatial extension, which is called PostGIS, and how this extension works. So you can basically create a table, like create table drivers, have two columns. One of the column is ID and second column is location with geography. And that geography type of column which basically stores location with latitude and longitude data. Now, when you're looking for nearest drivers from PostgreSQL, you fire the query like select ID and you pass latitude longitude with SG distance as dist from drivers table, and based on this, it will give you nearby drivers from this query. Now, what are the advantages of PostGIS? One of the advantages, it is SQL-based, so very easy to implement, easy integration. Second, it is ACID compliance, and there are certain limitations with this one too. One of the limitation is slower for high throughput systems. Second is harder to scale horizontally. So in this case, PostGIS is better for analytics regional data, but not real-time matching. Now, let's look into our third technique, which is called quad trees. How quad tree works and what it is. So quad tree is basically a tree-based spatial partitioning structure. It basically partition each region in 4 parts. So let's assume this is a world map where we will split the region in 4 parts. So when you're looking for drivers in New York City as an example, and this is New York map, in that case, first it will split the region into 4 parts. Then let's assume that we are looking for like random variable I will pick, which is like k is equals to 4. In that case, it will keep splitting region until I get the results less than 4. So this is one of the region where we have only 3 drivers, so it won't split the data of more. But in this case, when you see it, right, there are like more than 3 drivers here. So it will keep splitting the region until we get like a small region where we can find our matching driver criteria. There are a few advantages of using quad trees. One of the advantages is it is very efficient for special queries. Second, it's natural hierarchical partitioning by region, and it can dynamically adapt to driver density. There are also certain limitations with this too. One of the limitations is it is more complex to implement in distributed systems. It's harder to keep updated when driver locations change frequently, and it requires balancing and reindexing for high mobility data. So now you understood all these 3 techniques, and let's discuss about our trade-offs. To finalize, like more focus the best technique in our case. So for trade-offs, and before I go for it, I will also let you know that many times in system design interview, they ask like, what are the trade-offs you are using it and why? And you should be able to explain the reasons. So here we will understand trade-off in 4 aspects. First, speed, which is like if you compare Redis versus Post versus quad tree, Redis Geo works very fast compared to other 2 techniques. In terms of scalability, Redis needs medium effort compared to PostGIS and quad tree. In terms of updating cost, Redis has the low cost versus in terms of use case, for real-time driver lookup, Redis Geo works the best, and for analytics or history, PostGIS works best, versus if you want some matching algorithm implementation, then quad tree is the best solution. So in our case, we will go with Redis Geo. Now let's discuss about hotspot problem. What is a hotspot? In Uber-like system, hotspots occur when many riders in one small area, like stadium, concert, airport, request rides simultaneously. Many drivers update their locations around the same hotspot, and system components like Redis DB APIs handling that region becomes overloaded. Why it's a serious problem? So let's consider an example. After a concert ends, 50,000 people open Uber and tap request to ride. In that instant, Redis queries back for that region. Matching service tries to locate nearby drivers, and notification system filters drivers with requests, databases bursts of rides, and in terms of result, basically like latency spikes, timeout, or system crash. So let's look into at each level how hotspot appear in the system. At API gateway level, basically there is a certain burst of write request which will impact our overflow. At find write service, many geo queries for same region which will impact CPU or memory pressure. At Redis cache level, high reads plus write stored for same city or zone, which is basically like impacting our node CPU saturation. From matching service side, basically like too many concurrent match operations which might turn into thread pool exhaustion. And at notification service, too many push notifications which might impact in terms of delivery delay. And at database level, basically like spikes in writes, forwards, and driver updates. So overall, like at each level, there is an impact. And very quickly, I would say like we should also have some type of method to detect a hotspot. Basically, we should implement matches or telemetry. For example, we should have higher edits read, write, QPS for a specific region key, abnormal API request straight from same latitude or longitude range, or CPU or memory specs in one node. We should have telemetry on this one. And we should also have rate monitoring, which is like we can use Grafana dashboards for requests per city or region, and we should implement alerts when traffic exceeds threshold. This is just in terms of detecting a hotspot. Now, let's handle hotspots at multi-layer defense. And there are multiple techniques. Layer 1, which is like load balancing and throttling. So, there are multiple techniques at this level 2, which is like we can have smart load balancer, which will route requests evenly across multiple backend nodes. We can use region-aware load balancing and requests to the nearest cluster. Then also we can implement request throttling at API gateway level, which is basically like enforce per user per region rate limits. As an example, no more than 5 write requests per minute per user. Another way is like we can also implement queuing from find write service to matching service and from matching service to a notification service. So that way we do not overwhelm matching service or notification service data. So here I would suggest to implement queue. So instead of processing all requests immediately, we will queue them through Kafka or SQL, or we can also have PubSub. And matching service will consume requests gradually instead of having whole bunch of data in one go. There is a trade-off by adding queue, which is basically like there will be a slight delay but prevents total overload. Now layer 2, which is like geopartitioning and dynamic sharding. So what are the concepts, which is basically like partition cities into smaller geocells or zones, and each zone's data is handled by its own redis or cache partition. Then layer 3, which is like hard cache offloading. So for cache, basically like not just redis, we can implement multi-tier caching, which is like tier 1 redis, tier 2 memcache, tier 3 CDN or edge case for static data like search pricing zones, memcache, which is like for read-heavy hotspots. So these are like multiple layer we can implement for caching. Then layer 4, which is basically like matching service load control. For this one, we can have multiple techniques. One is like batch matching. So instead of matching each write individually, we group requests in 1 to 2 seconds batches and perform batch geo queries instead of match like per query, like per write. Another technique is like rate limiting per zone. So matching service caps concurrent match operations per zone. Another thing is like we can also implement auto scaling for each server. So whenever there is a high load, basically like if we have auto scaling implemented for all API servers, whenever there is a traffic, it will auto scale to servers. So these are the techniques in terms of how to handle hotspot. Now let's discuss about consistency. Consistency is very important in overdesign. Why? Because there might be a chance that if we don't have consistency, there might be double booking. So let me go in detail. When a matching service is finding rides and assigning drivers, many riders may be matched to the same driver if the driver is physically near several riders. Multiple matching service instances query the same driver pool, or driver availability data is slightly stale. So if 2 riders are matched to the same driver before the driver accepts one ride, double booking happens. And this will lead to bad user experience, inconsistent system state, and failed payments or cancellation. So the challenge is to ensure that at any moment, a driver can only be assigned to one active ride. So very easily this happens in the system. Basically, it happens exactly at this service level, matching service. And as I mentioned earlier, this is the brain of the system because it has a lot of logic and data and algorithm. Now, how do we prevent double booking? How do we make sure our system is consistent enough? So step 1, we can have atomic state transition at matching service level. Each driver should have a state in the system, and the state will go from offline to available, available to assign, assigned to on trip, and on trip to completed. The matching service must ensure that Only drivers in available state can be matched. Once a driver is matched, the state automatically transitions to assigned. If the ride is cancelled before the driver accepts, revert it to available. And this simple conditional update pattern works beautifully. If all services stop to the same TB or stock of digital cache, this will work out perfectly fine. Now, second thing is, we should also mention, or we should also make sure that consistency is maintained at cache level as well. So, Redis-based distributed locking we can use here. If we are using Redis for driver state, we can use atomic locking to prevent concurrent assignments. In Redis, there is a command called set if not exist. We can use that when the matching service wants to assign a driver, we just use this command. If this returns true, it means the driver lock is acquired for that ride, and proceed to mark driver as assigned and send ride notification. But if this command set if not exist is false, it means another process already locked that driver. And then you set an expiry to avoid deadlocks. Once the ride is confirmed or rejected, we can use the command to delete the release the lock. And this will guarantee only one service instance can hold a driver at any time. Now let's look into scalability. We need to consider our scalability almost at each level. Like in future, if we want to scale the system to support 10 millions of users or 10 times more traffic than what we have now, then we need to consider at each level how do we scale the system. So let's start first with API gateway. At API gateway, basically like we can have stateless gateways, multiple gateways, instance behind a load balancer. Then we should also implement GeoDNS load balancing, basically like route users to the nearest DT region gateway. Another way to handle is have CDN edge offloading. We should offload static access to CDN. Now, at matching service level, how do we make sure that we can scale this one too? So we should have partition matching service by region. So let's say like there are big cities, just as an example, like NYC, London or Tokyo, we should have match service like match NYC service, match London service, so that we like for each region, we will have its own matching service, and each service only processes rides or drivers in its geo shard. We should also implement a partition by geo hash, basically like split area into smaller zones, and each service instance handles only a subset of zones. At queue level, we can also decouple our ride requests go to Kafka queue if it is Kafka, and we can implement auto scaling at queue level. And for database layer, we should use shard by city ID and region ID. City ID or region ID. And each city cluster has its own DB instance. Even for read or write, we should have replication as well. So for read, we should have separate database, and for write, we should have separate database, so we don't overwhelm the database system. Alright, let's wrap this up. When thousands of riders suddenly request rides at the same time, say after a big concert, Uber system can't just handle every request instantly. That's where this multi-layer defense kicks in. At the top layer, the API gateway uses smart load balancing and rate limiting to stop overloads before they hit the core system. Then instead of sending every request directly to the matching service, we use message queues between find ride to matching service and matching service to notification service. These queues act like shock absorbers, smoothing out massive traffic spikes so services process requests gradually without crashing. The matching service can scale horizontally, consume requests at a steady pace, and still provide near real-time experience to both riders and drivers. Finally, at the driver end, push notifications stay instant. So from the user's perspective, the system just feels magically fast and reliable. So that's how large-scale systems like Uber handle certain services, using layer throttling, queuing, and smart route distribution to stay fast, available, and scalable. If you enjoyed this deep dive, then don't forget to like, subscribe, and check out the next video in this series. Thanks for watching, and I will see you in the next one.